All right. So today we're going to talk about how to, first of all, identify whether an ionic bond or a covalent bond is present. We are also going to then show how to transfer electrons from one atom to another atom. Now, first things first, ionic bonds. Ionic bonds are bonds that occur between a metal and a nonmetal. And covalent bonds are bonds that occur between two or more nonmetals. So that's the first indication of how we identify an ionic bond versus a covalent bond. The other thing that's really important is that in ionic bonds, electrons, that's an electron, is transferred from the metal to the nonmetal. So electrons are transferred. In a covalent bond, the electrons are shared. So I would have like one electron here, another atom here, or another element here. So I might have like element A and element B, and the electrons will be shared. Now, we're not going to spend a lot of time showing how electrons are shared in this unit because we have a whole unit dedicated to it later this year. So we're going to really focus on ionic bonds today and the transferring of electrons and how to draw them. But before we jump into that, I want to recap. So here we know that ionic bonds occur between a metal and a nonmetal. And covalent bonds occur between nonmetals and nonmetals. So those are the things that we have to keep track of. The other two things that we need to be able to remind ourselves of is that in ionic bonds, electrons are transferred, and in covalent bonds, electrons are shared. So a couple of examples to go through here. I see that sodium, if I grab my handy dandy periodic table, is in the first column on the left-hand side. So that tells me that it's a metal. And I see that fluorine is in the 17th column on the right-hand side. So now I see that as a nonmetal. So that alone tells me that it's an ionic bond. And I remember from the slide above that in ionic bonds, electrons are transferred. Now, in the next example, nitrogen and oxygen, I see that nitrogen is in column 15 on the right-hand side, so that makes it a nonmetal, and oxygen is in column 16 on the right-hand side, so that makes it also a nonmetal. And if that's the case, then that tells me that I have a covalent bond. And when we have a covalent bond, we know that the electrons should be shared. Now, what I'm going to do is I'm going to give you, a minute or two to go ahead and work through the next three. And while you're doing that, the next three. And so then that'll give us an opportunity to practice, and then I'll check your answer. We'll go through the answers in a second. So go ahead and identify the type of bond that would be present between CO2, MgCl2, and HF. All right, so I'm going to take a couple of minutes to go through this. So I see that carbon is in column 14 on the right-hand side, and oxygen is in column 16 on the right-hand side. That gives me an indication that they are both nonmetals, and that makes them covalent bonds. And that would tell me that the electrons are transferred. Not transferred, they're shared. The next one, magnesium is in the second column on the left-hand side, so that makes it a metal. Chlorine is in the 17th column on the right-hand side, so that makes it a non-metal. And so that tells me that it is going to be an ionic bond. And then that would tell me that electrons are transferred. Now, the last one is a little bit tricky, in large part because hydrogen is on the left side of the periodic table, but it technically is a nonmetal. Fluorine is in column 17 on the right-hand side, and that's a nonmetal. So that makes this also a covalent bond. And then that would mean that the electrons are shared. So hopefully that didn't seem too incredibly difficult. All you're really doing is identifying where the electrons are or where the atoms are on the periodic table, whether they're a metal or a nonmetal, and then you're identifying if they're, and that helps you to identify if it's ionic or covalent. Questions? All right, so I don't see any questions, so we're going to go on to the next slide. And in the next slide, what we're going to talk about for a second here is something called Lewis dot structures. Now, Lewis dot structures are an easy way to represent the number of valence electrons that an atom has. So when we talked about valence electrons, we remember that valence electrons were in the outermost energy level, and the number of valence electrons that an atom can totally have, that an atom can have total, is going to be 8 valence electrons. Now, when we draw Lewis dot structures, we're only drawing or representing the electrons that are in the outermost energy level or shell, those valence electrons. So if I were to draw an element and draw the 8 electrons, I would draw them in sort of a pattern. So it kind of looks like this. You'd go up, top, bottom, left, right, top, bottom, left, right. So you want them to pair up, really, is what's happening. Some textbooks or some teachers, they kind of show you this pattern by going 1, 2, 3, 4, 5, 6, 7, 8. And actually, to be honest, the order in which you do them is not really important to me, as long as you don't double up electrons until each of the 4 sides of the element symbol has had at least one. And we'll kind of go through a couple of examples like that in a minute. So let's practice. I'm going to start with the element sodium, which has the symbol Na. And if I locate sodium on the periodic table, it's in the first column. It has, and I know that it has 1 valence electron. So all I'm going to do is I'm going to go and write the symbol for sodium, capital N, lowercase a, and I'm going to add 1 electron, and I'm going to start in the top, and that's it. I'm done. Another example that we could do would be something like, I don't know, let's do nitrogen. Now, nitrogen is in column 15 on the periodic table on the right-hand side, and that means that it's going to have 5 valence electrons. So I'm going to start by writing nitrogen symbol, which is capital N, and then I'm going to add electrons. 1 on the top, 1 on the bottom, 1 on the left, 1 on the right, and then I'm going to double up on the top. Okay. Notice that when I did that, I added a top one, a bottom one, a left one, and a right one before I doubled anything up. And that's really the key on these. The last one we're going to try here is we're going to try fluorine, okay, which has the symbol of F. Fluorine has 7 valence electrons. So when I go to draw fluorine, I'm going to draw the symbol for F, symbol for fluorine, which is a capital F, and then I'm going to put 1 electron on top, second one on the bottom, 1 on the right, 1 on the left, so that's 4. Double up on top, double up on the bottom, so that's 6, and then I'm going to add 1 more on the left, so that gives me 7. So now fluorine has 7 electrons around it, 7 valence electrons around it, and that's all that we need. Any questions about drawing Lewis dot structures? Yeah, I mean, like I said, I usually go. I guess I don't know. I usually go top, bottom, left, right, top, bottom, left, right, and you could have put it in the 7. It's fine, as long as you don't double. Like I said, the only rule is you don't double them up until you've had 4 on each side. No, but usually we try to separate. We try to spread them out. So another one that we'll do a bunch of today would be like oxygen, right? So let me see if I can squeeze oxygen. So oxygen has 6 valence electrons, and when I draw that, I would usually draw it as top, bottom, left, right, top, bottom. And the reason why is you want to spread the electrons out kind of as much as you can, because they are negative and they want to be as far apart from each other as possible. So usually going like 2 on the top and 2 on the right side is kind of frowned upon, but it's not that big of a deal. Okay. All right. Now, the next thing we need to do is talk about ionic bonds and transfer. So first thing, to refresh our memory, I know it wasn't long ago, but in an ionic bonds occur between metals and nonmetals. And electrons are transferred. Okay. Now, the 2 elements that we are going to be looking at today are lithium and fluorine. And so I know that lithium is in the first column, so that makes it a metal. Fluorine is the 17th column, so that makes it a nonmetal. I know that because lithium is in the first column, it has 1 valence electron, and I know that fluorine is in the 17th column, so it has 7 valence electrons. Okay, so these are the things that I know for sure. Now, the other thing that I know, and this is going to go back in time, but lithium has an electron configuration of 1s2, 2s1, and fluorine has an electron configuration of 1s2, 2s2, 2p5. And the reason why I'm showing you the electron configurations from what feels like forever ago is it helps me to explain, I think, what's actually happening here. So in our process, what we're going to do is we are going to draw Lewis dot structures for each of the atoms that are present. So in this case, I'm going to draw my Lewis dot structure for lithium. And up until now, I've been drawing all the electrons as dots. I'm going to draw this one as an X, and it also helps to illustrate what's happening here. So lithium's 1 electron is an X, in my opinion. Okay. Now, fluorine has 7 valence electrons, so I'm going to still draw those as dots. 1, 2, 3, 4, 5, 6, 7. Now, the next thing that we have to do is we have to show that electrons have been transferred. So lithium is going to give up its electron and transfer it to fluorine. Remember, metals will transfer to nonmetals, but nonmetals don't transfer to metals. So this lithium electron is going to go right about there. Now, when I draw the result, actually, before I do that, so what happened is this electron here got transferred to that spot there to give fluorine a noble gas configuration that makes it look like neon or behave like neon. And because lithium got rid of that electron, it now has the noble gas configuration like helium. So when in terms of transferring electrons, all these atoms are doing are attempting to get to a more stable arrangement. And the more stable arrangement is the full octet. Okay. So when I rewrite these as my result, I'm going to have lithium, and lithium got rid of an electron, so it becomes a +1. And fluorine, I'm going to draw with all the electrons around it, including the one that it gained, and I'm going to say that it's a -1. And when I go to write the formula, I take the elemental symbols and write them next to each other. And then I count. I have 1 lithium and 1 fluorine. And in chemistry, when there's a 1 value, we often don't write it. So it's just going to become LiF will be our final answer. So when drawing these structures, you have to, first of all, show the transfer with an arrow. Second of all, you have to identify what the charge is going to be. And then thirdly, you have to write the structure or write the chemical formula representing the number of atoms that are present. So any questions here before we go on and try another one? Okay. So sodium, I know to be a metal. Sulfur, I know to be a nonmetal. Sodium has 1 valence electron. Sulfur has 6 valence electrons. Now I'm going to write their electron configuration, which is 1s2, 2s2, 2p6. 3s1. And sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. Next thing I'm going to do is I'm going to write the Lewis dot structure for sodium. So I'm going to draw a sodium with capital N, lowercase a, and I'm going to put an X on top of it for that 1 valence electron. I'm going to write sulfur with its 6 valence electrons, 1, 2, 3, 4, 5, 6. And then what I'm going to do is I'm going to show that electrons are being transferred from the metal to the nonmetal. So really, this electron here is being transferred here. Okay, and up in my electron configuration, this electron here is being transferred here, and now sulfur has 3s2, 3p5. So if I redraw what I already have, I have sodium that lost an electron, so it's going to become a +1. And sulfur, as it's drawn, looks like this. Now, sulfur doesn't have those 8 electrons, and as a result of it not having those 8 electrons, it's not satisfied. So I can add another atom, but I can only add atoms that are present. I can only add sodium or sulfur. I can't add iron. I can't add carbon. I can only add sodium or sulfur. Now, the thing of it is that I'm going to only add the atom that can do the transferring in this case. So because sulfur is short 1, so I'm going to add a sodium. And because sulfur is short one, I added a sodium that shows that the electron transfers to sulfur. So now at this case, I have a second electron that sulfur gained. And as a result of that, sulfur now has a -2 charge. And my added sodium has a +1 charge. Now, the issue is that, so I added a second sodium, right? And so when I did that, this now becomes 3p6. And so we have a full outer shell here of 8 valence electrons. So that sulfur is happy and satisfied. And when we got rid of the 3s1, this is now our neon configuration. So the sodium is in a good place. So now the last thing that we're going to do is we are going to write our symbols next to each other. So I'm going to write Na and S, and I'm going to count the number of Nas, which in this case is 2, and I'm going to count the number of S's, which is 1. And I don't write ones when I'm doing this, so I'm going to rewrite this to be Na2S. Questions here? Okie dokie. There's one more example. I would like you to give it a shot. I would like you to try it for now. Okay, so go ahead and give this a shot. I'll wait quietly. Okay. I see that a lot of you are working on this and it looks like you're doing a pretty decent job. But I do want to make sure that we get through this one for a good example at the end here. So here we go. I know that aluminum is a metal because it's in the 13th column on the left-hand side and it has 3 valence electrons. I know that oxygen is a nonmetal because it's in the 16th column on the right-hand side and it has 6 valence electrons. I know the electron configuration for aluminum is 1s2, 2s2, 2p6, 3s2, 3p1. And oxygen is 1s2, 2s2, 2p4. So I'm going to start with my aluminum. And I'm going to draw aluminum to have 3 electrons. And I'm going to add oxygen, which will have 6 electrons. And then I'm going to start showing transfer. So I'm going to have 1 electron from aluminum go to that oxygen, and another electron from aluminum go to this oxygen here. Okay. Now, at this point, my oxygen has it's 6 electrons. So 1, 2, 3, 4, 5, 6, and the 2 electrons that it picked up from the aluminum. And when it picked up those 2 electrons, it got a charge of -2. The aluminum, however, still has an electron to give. And as a result of it still having an electron to give, we have to add an atom. And in this case, I can't add an aluminum because it doesn't want to give electrons to itself. So I'm going to add an oxygen, which still has 6 valence electrons. And now I'm going to transfer that 1 lone electron from aluminum to oxygen. And at this point, my aluminum is pretty proud of itself because it has gotten rid of 3 electrons, so it has a charge of +3. The oxygen that I just added has its 6 electrons plus the 1 that it just gained. So it doesn't have 8 valence electrons, so we need to add something else. So at this point, the only thing that we can add is we can add an aluminum. And the only reason why I'm going to add another aluminum is because I can't add an oxygen because oxygen doesn't want to add electrons to itself. So I'm going to transfer an electron to that oxygen from my second aluminum that looks now like this. So in this instance, my oxygen now has a -2. However, I have an aluminum that has got extra electrons it wants to get rid of. And when I do this one in class, this is where people start to groan. So I'm going to add a third oxygen here to look something like this. And then I'm going to transfer an electron from the aluminum to the oxygen here and transfer an electron from the aluminum to the oxygen here. So now my aluminum, right, my second aluminum that I added has lost its or transferred all 3 of its electrons, so it becomes a +3. My third oxygen that I added now has its original 6 plus 2 from the second aluminum, and it now has a charge of -2. So when I go to write this chemical formula, I'm going to take these symbols, aluminum and oxygen, and write them side by side. I'm going to count up the number of aluminums. There's 2, so it's going to become Al2. And the number of oxygens, there's 3, so it's going to become Al2O3. And that would be the answer for that particular one right there. Now, so what happened here, hopefully you can see this, is that the 3 electrons from aluminum kept transferring to the oxygen, so on and so forth. And if we did that eventually until the positive charge equaled the negative charge. So really in reality, I have a +6 and a -6 adding up and eventually equaling 0. And that's that's pretty critical as well. Now, your homework for the evening, which I just posted on Google Classroom for you, looks something like this. It's Unit 5 Worksheet 2. There you have to identify if it's ionic or covalent bonds. You have to then draw some Lewis structures, and then lastly, you have to draw some. You have to show some element transfer in ionic bonds. So very much like what we did in the notes. Any questions now? Yeah, for sure. So in example number 3, I started with 1 aluminum and 1 oxygen, and I transferred 2 of the electrons from aluminum to that oxygen. That first original oxygen then had 8 valence electrons around it, and it couldn't take any more. My aluminum had 1 electron left, and I can't leave it like that. So I had to add another oxygen. And when I added a second oxygen, I was able to transfer the electron from aluminum to that second oxygen. But that oxygen only had 7 electrons then. And as a result of it only having 7, I needed to add another aluminum. And when I added that aluminum, I then transferred 1 electron to the oxygen. So now the oxygen had 8. But the aluminum had 2 electrons still, and we can't leave it like that. So I had to add a third oxygen, and then I was able to transfer all of my electrons, my remaining electrons, to that oxygen, and then everybody had 8 electrons. Does that make sense? Mm-hmm. Yep. Yeah, don't like when you're trying this for homework this evening, just do your best, do the best you can. I know that this sometimes can be a little tricky at the beginning, but we'll definitely talk about it and spend some time going over it tomorrow. All right. We are butting up against the end of the hour, so if you have any questions, you can stick around and ask. Otherwise, you have the remaining minute or so to work on your homework, or you can leave.